To build some AI system, we need to define something mathematically formalizable. At the same time, we have some abstract goals that we want to reach. Sometimes this formalization of the goal mismatch actually want to do. One of the keys to mitigate teacher hacking is diversity of the data. One of the ways to increase diversity of the data is to increase diversity of prompts. Rewards hacking in general, it's the phenomenon, and the model was trained to do basically one thing that make a lot of sense, in some sense, a lot of sense to train from our perspective. For example, like I have very good GIF that shows one essence of this phenomenon. I really like it when talking about reward hacking. This phenomenon happened in traditional RL, even without any language models. So in a traditional RL, we want to define some reward to somehow encode our abstract goal. So we have two things. To build some AI system, to build something, we need to define something mathematically formalizable. And for example, and at the same time, we have some abstract goals that we want to reach. Sometimes this formalization of the goal mismatch what we actually want to do. Like on this small GIF, you see that like the abstract goal for training this small robot was to balance the ball on the top of this robot, but eventually the robot finds another way to fulfill his reward maximization problem. So the robot wants to maximize reward, and we give him +1 reward each second while ball is not on the floor, and he found some way to hack this reward and to achieve this goal differently.
What was the hacking in this case?
In this case, the ball is not balancing, but it just goes to some hole. Then it's formally goal satisfied, but it was not our initial abstract goal.
What is the main challenge? Why researchers struggle to find the correct reward for agents to minimize the reward hacking? What is the root cause of that problem?
This type of reward hacking. So here we have like a lot of different types of reward hacking in the end of the day. This one is like goal mismatch. It just needed to somehow design another reward function. In the context of language modeling, for example, reward hacking happens not from that we abstractly define our reward differently, but we train our reward function. And in the case of training, it is much harder to control what exactly reward we want to have. So for example, here we can also put, for example, negative reward if the ball is somehow fixed, or like try to fix it somehow manually. In the case of language modeling, our reward function should be defined on any possible sentence in the end of the day. And we need to train model to do it, because it's impossible to do manually. Of course, there's a branch of error verifiable reward. We won't talk about it. But in traditional reinforcement learning from human feedback, we train our reward model somehow. And this training causes some problem because we cannot cover all the space, we cannot cover all the possible sentences.
Do you think in considering like RLHF that the problem with mismatched reward, it sort of will be persistent, especially considering like the deployment of AI agents that basically already happening?
I guess yes, because like this problem is extremely connected to the problem of uncertainty estimation for language models. And this problem is extremely difficult. So to properly estimate what models know, what model does not know. For example, in this case, we can somehow control the rewards. Reward hacking is extremely connected to uncertainty estimation because we need to understand what model knows, what model does not know. For example, theoretical ways to avoid reward hacking is to make this reward pessimistic in the sense that if we don't know, uncertain about what's happening on this sentence, we should put very small reward, and we should penalize for not knowing exactly what's happening here. And since uncertainty estimation is also hard, I guess that the reward hacking should be also hard to overcome.
In your work, you're exploring the teacher reward hacking. Can you share the origin of your work? Like what inspired you to work on this? And like how like this idea of exploring the teacher hacking came into place?
Yeah, actually, the story behind this paper is quite funny. So I was not intended to study exactly teacher hacking. I was doing some distillation experiments to understand the future direction. And after I was training this thing, so we first like trained in this setup that we will talk later, to see some other phenomena, to more or less like to do another type of work. During this training, I just noticed this effect. If you use like online generation of data, if data is not is always fresh, and you don't reuse the same data for a lot of times, your curves for like your error from point of view of your teacher, your rewards that you observe, and your ground truth reward, some type of ground truth reward, both improves. Like this losses goes down, everything is super correlated, everything's super nice. But afterwards, I just thought about, okay, but in practice, people just reuse the same data for a lot of time. What will happen if I will do this pipeline? And I just observe this effect from respect of the teacher. So the distance to the teacher model decreasing, but the distance to the Oracle model at some point start increasing. And afterwards, we thought about analogy for this effect, and we end up with the term teacher hacking.
Can you explain like so in your paper, you're like, there's an Oracle model, there's a teacher model. So what is the Oracle model?
The Oracle model is some well-trained, already pre-trained, already fine-tuned model that assumed to generate something that's close to ground truth generations. So actually, we wanted to study distillation in some very controlled experimental setup. Then we can know everything about everything. So it was initial goal. So we started, of course, with some very simple, completely synthetic things with Gaussians, things like that. But it is impossible to see a lot of effects on Gaussians, of course. So that's why we moved to language modeling. And to preserve this controllability of setup, we replace our human generations by some fixed, quite powerful model compared to student and teacher.
Which model did you use as an Oracle model in your experiment?
In the distillation loss that we used everywhere, we need to estimate scale divergence between next token distributions. That's why we need the same tokenizer for all the models. As a small model, we use T5 because it's quite small and it's very easy to experiment with it, like to do a lot of ablations, to try a lot of things. We stick to T5 model and we use just quite large fine-tuned T5 with 3 billion parameters trained on a FLAN dataset.
Can you walk us through the design of experiment and so we'll better understand how exactly that was conducted.
So initially we have Oracle model that assumed to be ground truth. That means that if we do some training for teacher model, so the teacher model is already pre-trained model, so it has some general understanding about language, but we need to specialize it for our task. So we have some prompt dataset from the given task. For example, for translation, it's sentences in German that we want to translate in English, or vice versa. And given this prompt dataset, we generate completions using Oracle model. And we use this dataset to perform the first stage of SFT for teacher and for student. So we have some warm start, and teacher and student, in this case, also assumes Oracle to be ground truth because the SFT data will generate from Oracle. And afterwards, we perform distillation of the teacher to the student model using different type of losses, different types of data that's used during distillation. And for the next step of evaluation, we use access to Oracle model. So in this pipeline, we never touch logics of Oracle model. So Oracle only generates dataset and does not participate in the training of the student, only through the small Oracle dataset. But afterwards, we use Oracle model to evaluate the distance to this model. So to evaluate the quality of task completion.
It evaluates the quality of the task that student learned from the teacher, right?
And they both should learn it from Oracle. So first, teacher learns from Oracle how to perform the task, and afterwards, teacher tries to move this knowledge to a student. But also, students saw this data from the Oracle just to have fair experiment. In essence, they both saw the same data, they trained on the same data, but teacher is larger, it generalizes better. Student is smaller, generalizes worse, and afterwards teachers try to decrease the gap between the oracle and student by teaching the student.
What are the sizes of teacher and student models?
We have several different experiments in our paper. For students, yes, we use T5 base, T5 large. Oracle model is 3 billion model, and teacher and student is only pre-trained model with 800 million parameters and 250 million parameters approximately.
You decided to use the small model so like you can conduct experiments faster and like with less resources. That was the motivation of why you choose this.
Yes, and to train for longer time, because initially we observed this effect that it happens from 8-10 epochs of training, and it would be super expensive to do it on larger models. And especially since we need to have a gap between the models of these sizes, it might become much very expensive to do it, and it took a very long time.
When did the teacher hacking like come into place in this in this training?
These plots are much better showing this phenomenon.
Mm-hmm.
So basically here what we observe. Here we perform a distillation on summarization task. So we use the prompts, we have the large article, with instruction summarize it. Our T5 did summarization for the Oracle dataset. Afterwards, teacher-student trained on this small dataset. Afterwards, we use all the prompts from the exam dataset to perform distillation. Offline dataset, it is the dataset where all the completions for distillation was done once by the teacher. So we just fill the dataset of the size 200K. And we trained a lot of epochs on the same dataset. Online student, online teacher, it is then you use the same prompts, like prompts from the same dataset. We was not able to generate new prompts, new articles, but we was able to generate new completions, new summaries. So in case of student, and we can do it both by student model and both by teacher model.
Online data is like basically synthetic data?
All the data is synthetic, but offline dataset was generated once, and afterwards the same completions was reused over training. And online training, it means that if we sample batch of prompts, each time that we sample this batch of prompts, we generate new completions. So, and we can see here that's like train loss, like the most basic things, that it always goes down. That make complete sense. Proxy metric. So proxy metric, it is the distance to the teacher computed on the validation set. The model never saw these completions using proxy metric. And for this type of metric, like for this type of distance, for both for online generations, everything goes down, but also it goes for offline generations. If we reuse the same data, it starts stagnating. It's not goes down as fast as for online data, but it's have diminishing returns, but it still have potential to continue training. So in the end, yeah, the little increase, it is just due to averaging. So, but from point of view of the golden metric, it is distance of the Oracle model. If we reuse online data, we continue to generalize. But if we use offline data, if we see the same context over and over again, starting from 10 epochs, our KL start increases. Or else it stagnates from 3 to 10 epochs when the proxy metric, the distance of the teacher, continue to decrease, not so fast, but continue to decrease. But golden metric at the time stagnates or even a little bit increases, and afterwards it starts increasing more. It requires a lot of training. Eventually it will happen.
It's just a clarification. I realized as I was watching the previous slides, I was interpreting it one way, and then I realized maybe I was misinterpreting it. So the two models are both training on the same Oracle training data. Is that only for supervised fine tuning, so that the teacher and student model, before you've done any of this, they were each pre-trained? So you were using, say, Gemma 2 and GPT-4 as the student and teacher, and then you were fine-tuning on top of that? Or is that what's going on?
Yeah, your understanding is completely correct. First, they use the same data, and afterwards we do additional fine-tuning by distillation.
So we expect that from all that pre-training that's not shown here, the teacher has something to contribute to the student.
Yes.
Can you please elaborate teacher hacking? Because I'm not sure, like I understood like how it occurred. during the experiment, like how you saw that the teacher hacking is happening, like how through what output did you realize that okay the teacher hacking appears?
For me, the main indicator it is the right plot, or for example, this plot is I think for just checking does it exist or not is more clear. So on the x-axis, we have a distance to a teacher. Distillation typically goes from left to the right because we becoming closer to our teacher model. On the y-axis, we see golden metric. Golden metric is a distance to our ground truth distribution. And initially, training starts here, like for the more darker dots. It starts here. First, initially, it optimizes both proxy metric and golden metric at the same, like not the same pace, but like say optimizes both. But afterwards, we see the U-shaped curve. That means that we continue improving from point of view of proxy metric, but from point of view of golden metric, we start degrading, starting from some point. And it was like initial plot, then I saw that, okay, something goes in some sense wrong here. If you make the same plots for online data source, they will be completely linear. You will never see something like U-shaped curve.
I was wondering if I could try to summarize what I think seeing, and there's a couple gaps I have in this, and I might be misunderstanding something, but the training loss here is something along the lines of both models are being adjusted to try to get the student's beliefs touch the teacher's beliefs.
Correct.
Right. Okay.
Yes.
And of course, they become more and more in agreement as it goes on. The golden metric is something along the lines of how well the student performs on an actual test set of problems, right?
Here I can put additional clarification. So both proxy metric and golden metric,
Yeah.
it's about test set. But proxy metric measures agreement between student and teacher on test set, and golden metric measures agreement between student and our ground truth in our controllable setup.
Right. Okay.
Between student and ground truth, yes.
So we're not actually seeing any changes to how the teacher is performing here, right? I'm imagining teacher hacking means the teacher is also adjusting some weight something and is becoming unduly messed up, trying to somehow align itself to the student during this. But we're not actually seeing the teacher changing here, right?
Yes, here only student is trained, teacher is fixed, so it shows this SFT data. It's initially better than student because it's bigger, it generalizes better, and afterwards teacher is fixed, and student tries to hack the teacher.
But the teacher's not changing.
No.
The student is hacking the teacher of the student becoming more consistent with the teacher's belief, but less consistent with ground truth?
Yes, exactly. This plot, it is like this proxy metric is agreement between teacher and student, and agreement improves. So this here axis like goes in the decreasing order. So first it's have a large disagreement, and afterwards disagreement becomes smaller and smaller. And the golden metric is agreement between ground truth and student, and it first goes down, and afterwards it goes up.
A lot of times when we see overtraining, right? Where it's just simply that we haven't had enough variety, of the real world. We're sure this isn't just like an overtraining thing, right?
The usual like overtraining, the usual overfitting would force this proxy metric goes up. It is a distance calculated on the test set, and it still goes down with diminishing returns, but goes down.
Okay.
Then should we move forward to like medicating reward hacking?
And the first way how to medicate it was already shown. It is using online data, but it is extremely expensive. So because for each sampled batch, we need to generate new completions, and it takes a lot of resources. And especially it is expensive from point of view of latency because generation is autoregressive. And that's why, for example, we suggest also to use online student generation because student model is smaller. It's much cheaper to generate online data from students, especially when teacher becomes much larger. This also this thing was inspired by online policy distillation paper by my colleagues from Google. Let's do it here. Another thing how to medicate this thing is connected to diversity of the data. So here I just showing like one equation that's basically like we can test how diversity of the whole data set impacts training by just fixing the subset of prompts and generating more completions to study how diversity of the whole data set impacts the training. Return like to the original question, one step forward before the actual answering the question. One of the keys to mitigate teacher hacking is diversity of the data. In some sense, online generations of the data, it generates in some sense infinite diversity because we always generate new data. It is always new. It would be not infinite because there's not infinite ways to summarize something. But from practical perspective, it's almost infinite diversity of the data, especially since we use temperature sampling. So we was generating a lot of different summaries of the same text. As a way to mitigate teacher hacking, we can use different ways to increase diversity of the data. One of the ways to increase diversity of the data is to increase diversity of prompts. So if we use more diverse prompts using the same training budget, we can get better results. And we can reduce the level of hacking.
Can you give us an example of the diversity of prompts, like just to better understand, like what is the diversity of prompts could be?
We use like very simple setup. So we just more or less repeat the prompt several times. So just we have the set of prompts of size 200,000, for example. And afterwards we say, okay, how to test our hypothesis about diversity? We cannot generate new articles. Of course we can with a super large model, but if we want to keep the initial distribution of the prompts, let's take half of these prompts and make 2 completions for each of them. You have total data set will be of the same size, and you can treat like you just decrease diversity of prompts because you have the same prompt as data set twice. And afterwards, you can continue this procedure, and you can, for example, decrease size of the dataset in 5 times, generate 5 completions for each prompt.
Is there anything else like important, like as a conclusion, like that about this work that you would love us to take with us as a takeaway?
I would say that like the main conclusion is like diversity of the data is a key to overcome a lot of problems. It helps a lot with generalization. It helps a lot like with fighting this teacher hacking with a lot of phenomena. You can always like reuse the same data, but it can end up with something some phenomena like this teacher hacking, because if we would have like a lot of diverse data, we would never face it.